Hello, and welcome to this latest video demonstration of Icon Science's RokDoc software. Today we will be taking a look at the reservoir monitoring add-on for the reservoir characterization module. In this particular case study, we'll be focusing on an appraised oil field and wish to optimize the development plan by using 4D seismic data. We will define a shared Earth model where we can combine geological, geophysical, and engineering data, allowing us to generate forward models from the reservoir simulation and to extract information from 4D seismic in order to update the flow simulation. The 4D seismic method can potentially allow us to perform intra-well history matching of the flow simulation and ultimately enhance our ability to successfully site infill wells and optimize reservoir delivery. We have a number of appraisal, production and injection wells, multiple seismic surveys. We'll be focusing here on the eastern extent of the field, and multiple geocellular models. Horizons are available for key interfaces, and depth horizons can be extracted from the geocellular models. These geocellular models contain both static and dynamic geological properties, such as net to gross, porosity, saturation, and pore pressure. Dynamic data is indicated with a clock symbol in RokDoc. We're displaying the water saturation for a particular time step here. RokDoc is date aware in that the time step for any dynamic data can be selected, and the software understands that the values within the data update for that time step. A number of time steps from the water saturation within the flow simulation are being shown for illustration. Differences, or deltas, between time steps can be made, and the change in water saturation between the two dates is shown. The red colours indicate where water saturation has increased between the base and selected monitor date. For this field, 4D seismic has been acquired. The difference in amplitude is shown between the same two time steps as for the simulator water saturation. The seismic is SEG normal polarity, and the differences are always monitor minus base. Therefore, blue colours indicate a hardening of the response. What we will look to do is to understand the match or otherwise between the flow simulation and the observations in the 4D seismic. In the first instance, we can generate time-lapse seismic models by transforming the flow simulation into a 3D/4D synthetic. We can also define a space where estimates of delta water saturation and delta pore pressure can be generated from the seismic response, and ultimately used to update the flow simulation itself. This is the so-called closing the loop workflow. This is an example of a reservoir monitoring session. Any number of views can be defined simultaneously. Here we have an arbitrary line duplicated, two map views and a 3D view. The session itself is defined in depth as the geocellular models are defined in depth and sampled laterally onto the seismic grid. In the upper left section, the K index from the geogrid is shown. In the lower left section, the porosity from the simulation is displayed. The maps show the base date water saturation and the net to gross from the simulator. In order to add time-native geophysical data and to generate synthetic seismic models, we need to define a depth-time conversion. A number of options are provided. In this case, a series of depth-time horizons are specified, implying a constant vint per zone per trace. The structural model date is the date for which the depth-time conversion is valid, and the time shifts are calculated with reference to this date. Other controls on the session setup allow the mirroring of the flow simulation zonation and the definition of datums, which are important when defining pore pressure and stress trends. Once defined, any data can be displayed in depth or time. So depth-native reservoir simulation data can be displayed in time, and the time-native geophysical data can be displayed in depth. Clearly, the dynamic data in the reservoir flow simulation has a temporal element, in that the values within each cell vary with date. For example, the values for the flow simulation water saturation, shown in the left-hand map, are specific to the base date. Some properties, such as the net to gross, displayed on the right-hand map, are static, and will therefore not change with date. The flow simulation SW is now plotted in the upper left section. Every viewer has a date associated and a date selector. This selector automatically picks up the dates from the loaded dynamic data as shown in this list. Alternatively, a calendar selector is provided. If the session view date is changed, any dynamic data displayed will update to reflect this. The view date can be synchronized across viewers. Here we are displaying dynamic data from the flow simulation and 4D seismic data. The values in each view update to reflect the change in the view date. When performing 4D analyses, we look at differences or deltas between time steps. This function allows interactive differences to be calculated based on any dynamic data within the session. This might be flow simulation outputs, 4D seismic, or the product of dynamic rock physics. To begin with, we will generate a difference from the simulation water saturation. The differences can either be made as monitor minus base or monitor minus delta time. The monitor date is the view date, and the differences will update to reflect the currently selected view date. Once calculated, the recipe is saved in the tree on the left of each view. The difference in water saturation is now displayed in the top left section. The monitor date is currently selected for all views. This difference can also be mapped out. The values are calculated only on the selected data and not realized as a volume unless required. A difference recipe has also been generated from the 4D seismic and is now calculated on the data in the lower left section. The seismic data has already been time aligned and warped, with a time shift estimated between the seismic time steps or vintages. At this stage, we want to make a connection between the delta water saturation implied by the flow simulation and the observed 4D seismic difference over the same time step. The differences can be viewed on separate lines or overlain using a site quantity. This visualization option allows the user to view any data type or recipe within a sub-window. This window can be resized as required and moved across the section, allowing an in-depth visual comparison of the two data types. The delta amplitude from the 4D seismic is now plotted in the right-hand map view and can be compared to the delta SW in the left-hand map view. In this particular field development, no large changes in pore pressure are expected, so the comparisons here can be made with the focus on changes in saturation. In other settings, capturing and understanding the impact of changes in pressure and stress can be key. The first step is making a meaningful comparison between flow simulations and seismic, and to do this we need to generate synthetic seismic models based on the static and dynamic properties within the flow simulation. This is the so-called sim-to-size workflow. This workflow is also a key step pre-acquisition of 4D, where feasibility studies must be performed to understand if the 4D seismic technique can be of use in reservoir surveillance and delivery for a particular field. To perform this workflow correctly, we must develop a dynamic, predictive rock physics framework. This framework must be calibrated and tested at all the available well locations. The RokDoc software has best-in-class rock physics modeling capabilities. Please see the accompanying video that demonstrates the RokDoc rock physics module for more information. To propagate this model to a 3D 4D space, we need to set up three other models. The SDP model, which captures and allows manipulation of the dynamic data in the flow simulation, the fluid property model, which allows the definition of date-dependent fluid properties, and the dynamic 4D property model. SDP stands for saturation, temperature, and pressure. These data generally come from the dynamic flow simulation. The SDP model is defined on a zone-by-zone, date-by-date basis. Dates can be automatically populated from those available in the simulator or added by the user. For each zone and date, the dynamic geological data can be specified. In most cases, this is directly from a particular flow simulation run, but the SDP model allows any data to be selected. Background fills can be selected, which will automatically fill any null cells across the volume. Here we have specified three phases for the saturations, but a number of fluid types can be defined. There are even three undefined fluid types for added flexibility. For the pressure, both the pore pressure and confining pressure need to be specified, as the rocks are sensitive to changes in stress rather than the pore pressure. The main benefits of the SDP model are that multiple flow simulation runs can be stored and inserted into the 4D rock physics framework with ease, and that individual simulation runs can be edited by the user to perform what-if type analyses or to update the fluid simulation with additional information, for example from 4D seismic. The fluid property model is defined in a similar manner, zone by zone and date by date. The acoustic properties of the pore fluids are also dynamic in that they change during production as pore pressure and formation temperature change. The fluid property model is based on a selected SDP model from which the changes in temperature and pressure are extracted. The composition of the fluids can be changed temporally as well. So for example, the salinity and composition of the formation brine can be date dependent, and in this case the acoustic properties of the brine will vary based on changes in temperature and pressure and composition with date. The flag fluid property tables are used to calculate the acoustic properties based on these inputs with date. Populating the table is made easier with the provision of copy and paste functions. The final step is to define the 4D property model itself. This is where a number of geological and elastic properties can be defined as a recipe and populated across the model. This is where the static properties from the geogrid, the dynamic properties within the STP, and the dynamic fluid properties within the fluid property model can be linked with rock physics to generate date-dependent elastic properties. Again, this model is defined per zone. In zones above and below the reservoir interval, no flow simulation data is available. These zones need to be populated for a number of different modelling reasons. In the 4D property model, a number of options are provided. For example, we might choose to interpolate the well data within this overburden zone. A number of interpolation techniques are provided, including a range of geostatistics with a variogram analysis tool provided. Other possibilities include populating the non-reservoir zones and might include the use of depth trends or volumes from seismic inversion. Within the zones covered by the simulation, we want to combine the static and dynamic data from the simulation with rock physics to calculate date-dependent elastic properties. Here we have access to the same models as calibrated at the wells, and the parameters can be reviewed. It is also worth noting that the modelling can be performed per facies if required. The 4D property model automatically points to the data specified for the other inputs. The selected STP model automatically populates all of the dynamic data, and that is picked up by the rock physics. Swapping to a different STP, for example a different simulation run, is simply a case of choosing the new STP from the drop-down menu, and the inputs are automatically updated. We now have the ability to predict elastic properties from the reservoir flow simulation. Here the predicted VP is shown. The interpolation of well data is clear in the overburden and substrata, and the VP in the reservoir zone is predicted from the data in the geocellular model via the calibrated rock physics models. Again, the best approach is to review differences, and here a delta VP is shown, which is calculated as a recipe on the fly. Any number of interactive recipe-based, date-dependent synthetic seismic or impedance models can be generated now that we have the predictive rock physics framework in place. Here a delta synthetic full stack is displayed. This can be compared to the seismic amplitude difference. There are both similarities and differences between the two, and it's this comparison that is a key step in integrating flow simulation data with 4D seismic data. Noise clearly should also be considered, and a key piece of information in a pre-acquisition 4D feasibility study is what is the required noise level for the given expected signal. The reservoir monitoring add-on provides an interactive random noise modelling tool based on a signal RMS and target SNR, or NRMS. This noise field can be correlated both spatially and as a function of angle. The noise level is repeatable per date. A delta synthetic attribute with noise added is now shown. All of the steps are defined as chained recipes, so if any parameters are changed, the results will update. For example, if I specify a higher SNR, the difference section updates automatically to reflect this. A map extraction is now made that is consistent with the extraction made from the seismic difference. The recipe is now being run on the selected data. By inspecting the two maps, we can start to really understand the differences in the changes as predicted by the flow simulation and those observed by the seismic. We can focus in on areas where there are significant mismatches for further investigation. A number of options are provided, and some of the visualization options are shown here for illustration. For example, the site quantity can be used to compare delta SW from the simulator with the synthetic delta amplitude. Any of the recipes defined can be displayed in the 3D view. Here we see the delta SW from the simulator and the delta synthetic amplitude. The delta amplitude from the 4D seismic is also displayed in the 3D view. Many techniques for the optimization of seismic data for use in quantitative interpretation workflows are provided by RokDoc, and many of these are relevant for the optimization of 4D seismic data. Please see the accompanying video that demonstrates the RokDoc SDC or seismic data conditioning and inversion capabilities for more information. The section in the lower left now shows the delta amplitude from the 4D seismic before and after conditioning. The reservoir monitoring session is also the perfect space for integrating time-lapse seismic inversion data. Date-dependent acoustic impedance is plotted in the lower left section. A number of different techniques can be used to estimate changes in geological properties, for example delta SW, from changes in date-dependent seismically derived impedances within the reservoir monitoring session. A section through a delta SW estimate from 4D seismic is shown now. This can be upscaled into the geocellular model in order to update the flow simulation based on the 4D seismic response. The seismically derived estimate of delta SW is now rendered in 3D, and a comparison is made with that expected by the flow simulation. This estimate could easily be used to update the SDP model and therefore the synthetic seismic within the reservoir monitoring session. Beyond the amplitude differences, we should also review the time shifts implied by the model and those measured by the 4D seismic if available. The model time shift between the base and monitor are now plotted in the upper left section. These are calculated based on changes in velocity predicted by the 4D rock physics model and applied to the base depth time conversion. Optionally, these time shifts can also be applied to the two-way time framework of the model itself. The delta synthetic amplitude between the two time steps is now shown in the lower left section, and the synthetic time shift estimated between the same two time steps is plotted in the upper left section. These time shifts are now also mapped out in the right-hand map view. The time shifts estimated from the 4D seismic are also mapped out, and a comparison between the prediction and the seismic observations can be made. The aim of this demonstration has been to highlight not only the advanced functionality provided by the RokDoc reservoir monitoring add-on, but also to illustrate the integrated nature of the tool. Combined with the interactive recipe-based nature of the add-on, this allows seemingly complex 4D analyses to be performed both easily and interactively, and results generated in short timeframes. For more information on any of the functionality demonstrated here, please contact info@iconscience.com or visit our website at www.iconscience.com. Thanks for listening.